Okay, let's get started today. We have a couple of things on the agenda. The first is to wrap up command line arguments, and then we are going to proceed into 2D vectors, which are often called vector of vectors. Okay, and this also is related to the idea of 2D arrays, which is what the reading assignment for today covered. And we're going to start off with some lecture, then do an exercise from the book, a little bit more lecture, and then we're going to finish by having you work a top-coder problem, the first part of the top-coder problem that involves string streams and 2D vectors. The other thing we're going to talk about is type def. So that's the third thing on the agenda for today. So before we do that, I did want to quickly talk about some helpful things you can do for us when you post a question about code on Piazza. Okay, so let me actually just show the post I made to Piazza about that. Let's see. Not finding it. Useful things you can do to help. There we go. So, when you post your code to Piazza, if you just post your code and say, where's the bug? It's difficult for us to know where to begin, okay? We don't know what input is causing the bug. So one very helpful thing that you can do when you give us code is to tell us what is the set of input on which the code is not working so that we can try it on that code. Now, that may just involve telling us which test case of Dr. Planck's is not working for you. But tell us what portion of the code is not working. And if it's not working on a grade script, then tell us whether the issue is with standard out or standard error. Okay? Because some of Dr. Planck's test cases are error cases. So tell us whether we should be looking at your standard out or standard error files. Another thing that helps is if you give us a brief description of the problem. Presumably, you've done some debugging on it, okay? So tell us what you know about the problem. Maybe you think it's in a certain section of the code that you would like us to look at, okay? Maybe you're just totally baffled and it doesn't, the output just doesn't match what the input is supposed to produce. That's okay to tell us occasionally that you're just completely baffled, but sometimes you do have some idea of what the problem is. Third thing, we often need to run the program, okay? So that means we need to see all of your code, not just the code section that you think has the error, because it's often the case that the error actually is not in that section of the code. It's some other section of the code, and if you only give us that section of the code, we'll tell you it's right. And we can't help you because it turns out the error is elsewhere. So give us the entire program, and either copy and paste your entire program into Piazza or upload a file for us. If you give us a screen snapshot, it's no good. Okay, the TAs don't have time to type your program in. Okay, and if you give us a screen snapshot, we can't copy and paste a screen snapshot. So either copy and paste your entire program or upload a file, and please make sure you limit the that's a private question just for the instructors. Okay? Fourth thing, please provide some commenting. Okay? That's not so important for these first couple programs, but later in the semester, the programs get much more complicated. If you just give the TAs and me a whole 100 lines of uncommented code, that's next to impossible to debug. Again, the TAs have a limited amount of time, especially when you're posting on Piazza, so it really helps if you comment your code a bit so that we can see what's going on. And finally, when you post your question, please post it to all the instructors, okay? So that we all can see it and we all have a chance to comment on it, because that will get it back and answer to you much more quickly. And sometimes the TAs respond, but I'll see something additionally and I will make a additional response. And that happened already with one student. A student was using A to F. The TAs were trying to debug it and didn't realize that I did not want that approach being used. And so I kind of came in and said, look, don't use A to F. This is the way I want this done. Okay? So if you can do those things for us, and it's there in a Piazza post, it's labeled things you can do to help the instructors debug your code when you have a Piazza question, that would be very helpful. It will save us a lot of time and allow us to get an answer to you much more quickly. And believe me, that can make a difference, because especially if one of us is time pressed, we might have 5 minutes while we're looking at, and so we take a quick look at Piazza. If it's just a bunch of code and saying, what is the problem, we won't look at it. We only have 5 minutes. But if you say, this is the input, this is the output that was expected, this is where I think it is in the code, I have 5 minutes, then I may take a quick look and see, can I quickly debug it in 5 minutes? Okay, so help us so that we can help you. Yes?
So when we're sending the code to the instructors, is tar files just fine? Or?
We prefer .cpp, because most of these programs are just .cpps. Okay, later in the semester, you'll have a .h and a .cpp. If you can just upload both, it's a little easier. Okay, but if you give us a tar file, it's not the end of the world. Actually, tar files, now that I'm thinking more about it, do work pretty well, because then I just have to download one and untar it. So a tar file's fine. Yep, tar file works. Other questions about that? Okay, so switching gears then, last time I promised you a solution to the command line argument problem, and I will show it to you. So you were being asked to sum up command line arguments, and you needed to convert each command line argument to a number using an iString string. So here is the solution to that. You are going to iterate through the, why do I have I equals 0? Is that my, how did that even work? Ah, I know how that worked. Okay, you should not be starting at 0. You should be starting at 1. So you are going to be going from 1 through the number of command line arguments. And the user command line arguments start at 1. 0 contains the name of the executable. That would not be a number. And you can see that I declared an iString string. So the first thing we have to remember is to always clear our buffer if we're going to reuse it. And we're reusing it, so we clear it. Then we stuff the current command line argument into it. There's no need to convert that argument to a C++ style string, because the string function does that automatically for us. And then once it's in there, we can read that string into a number and add the number to our sum. Okay, so it's a pretty straightforward for loop. Counts from 1 to the number of command line arguments, and it converts each string to a number, sums up the number, and at the end we use printf. You were asked to print it in a field that was 5 characters wide, so %5d does the trick. Maybe it didn't. Yep, it said print the sum in a field 5 characters wide. So questions about that? Okay, I did want to point out one thing, because you will have this happening in your Lab 2 and Lab 3. So in Lab 2 and Lab 3, you also may be getting bad input for your pixels. Okay, it happens. You have to be able to check for bad input. And a lot of Dr. Planck's test cases check for error input. So in the lab, you can't just assume that the input for a pixel is numeric. So here, I'll show you what I would do if I couldn't assume that every command line argument was numeric, or in fact, what I should do, because users can give me bad data. In fact, the way hackers exploit programs is by giving those programs inputs that the programmer did not anticipate and did not do error checking for. So most hacker exploits involve exploiting lazy programmers that did not do sufficient error checking. Okay, so here I've been lazy because I'm assuming all my command line arguments are numeric. And a hacker could exploit that. So what I need to do is, before I actually sum it, I should say if that is a successful operation. So if it succeeds, then it's a number. Okay, but if it's not successful, then it's going to return false. The conversion operation will return false. Okay, and in that case, I would simply discard it. So else, I will discard it. So I'll have string bad input, and I will clear the buffer because the buffer is jammed, and then I will clear the jam by reading the bad input. So this would be required if I wanted to be able to withstand non-numeric input. This is removing the bad numeric input without actually processing it. Now, in Dr. Planck's lab, you'll find that he often has you print out an error message in this case. And you will need to look at his error message to determine what that error message should be. And we often get complaints from students saying, why doesn't he tell us what the error messages are? Okay, I get that complaint every semester that it's frustrating not knowing what his error messages are. Here's why he doesn't give you the error messages. If he gave you the error messages, he gives away what are the error conditions. And one of the purposes of this course is to get you to think about possible error conditions. If we simply hand you all the possible error conditions, you don't have to do any thinking. You'll just write your code to test for all those error conditions, and that's not what we want. So that's why he doesn't give you the error messages, because by giving you the error messages, he tells you what the error conditions are. We want you to think about what those error conditions are. Okay, that's what makes you a good programmer. No hacker in the real world is kind enough to say, oh, you should have thought of that error condition. Okay, actually there are white hat hackers who will, but there's a lot of black hat hackers who will simply exploit your not thinking about error conditions and will take advantage of that to do things like break into people's computers and encrypt their file systems and then demand ransoms. So we want you to start thinking about error conditions. Okay, and that's why we don't give you the error messages. Okay, you can always run Dr. Planck's executables. In every lab, he gives you his executables. You can run them on input to determine what the output should be. Okay, so if you figure out what an error condition is, it's easy to figure out what his error message is. Run his executable on the bad input and see what error message it produces, and then copy that error message into your code. So it's not that hard actually to figure out what the error message should be. Once you've determined what the bad input is, run his executable on that bad input. It will give you the error message that you should print. And you can copy that into your program. So questions about that? Yes.
How do you copy from the terminal into an file?
So copy and paste. You're running a Dell. On a Mac, it's simply from the terminal window. You just, here, let me make this one bigger. So if I have like G++O foo.cpp on the Mac, just clicking down and sweeping across will select it. Whoops. And then, whoops. On a Mac, Control-C will, whoops, is it Command-C? Command-C will copy it, and Command-V will paste it into your file. On a Windows, what is the Control-Shift-C will copy, Control-Shift-V will paste? Okay. So highlight with the cursor what you want to copy. Control-Shift-C will copy it into the clipboard. Control-Shift-V will paste it into BIM for you if you're in insert mode. Okay. On a Mac, it's Command-C will copy it, and Command-V will paste. Other questions? Okay. So we are going to be talking about 2D arrays and vectors today, and that's not the book that I need, so let me go back for a moment. And I don't need to create an account either. There we go. Okay, so two-dimensional arrays are conceptually like a table. Okay, and there's a lot of situations where we need to store tables in a program. You're already being introduced to that in Lab 2 with pictures. Images are two-dimensional, essentially stored as two-dimensional tables in a program, regardless of whether they're a PGM, the kind of files you're working with in this lab, or if they're a GIF file, or if they're a JPEG. They tend to be two-dimensional tables of pixel values. So we need to store them in memory as a table. In Lab 1, you had the checkerboard problem. It did not need to be stored as a table because you could just print off a line at a time and you didn't have to hold the entire checkerboard in memory. But if for some reason we had wanted you to hold the checkerboard in memory, let's say it was actually the game of checkers, then you would have used a table to represent it. So lots of situations where you need to store tables. Excel spreadsheets are tables. In the example in the book, they used an example of miles between cities as a table. So there's a lot of times when you want to store tables, and we do that with two-dimensional arrays or two-dimensional vectors. When we do that, we reference the elements using two indices. Just like with a one-dimensional vector, we use one index. The first index is the row, and the second index is the column, and you cannot change that. So the first index always refers to the row that you want, and the second one always refers to the column. So when I say my array 1, that's row 1, column 2, that's 2 equals 99, it gets the value 99. Now, in the computer itself, it's not stored as a two-dimensional array. It has to be stored as a linear array. And so what happens is all entries in row 0 are stored at first. Then all entries in row 1 are stored next, and so on. Okay, and that is called row major order. That's something you should write down. Row major order means that the row, that array is stored by rows. There is also column major order, which means that all elements in column 0 would be stored first. So if it was column major, then the result would be 55 would be stored first because it was the 00th entry. But then we would store next 10 because we were storing all elements of column 0. And so that would be, in that case, an empty entry because that is 10. And next we would have the entry, because that exhausts all column zeros, we would start with column 1. And that would give us another blank. And then we would store 77 because it was in, these are all column 1s, row 1, column 1. So that would be column major. Almost no modern language uses column major order. It's almost always row major order. Why do I bother telling you this? Because it matters for efficiency. It matters when you write the loops for accessing the elements in the array. There are two ways that you could write loops to, let's say I needed to print this array. There are two ways I could do it. The first is by going through the rows first. I could say for row equals 0, row less than num rows, r++, and then for column equals 0, column equals num columns, column ++, C out, this is my array, RC. That's one way to do it. Okay, that last thing that you may be having trouble, this is a C. So that's one way to do it. But there's another way to do it. You could also say for C equals 0, C less than the number of columns, C++, for R equals 0, R less than the number of rows, R++, C out, my array, R and C. And now this is going to produce a somewhat different output because it is column-centric rather than row-centric. So the first one we say is column-centric because it starts with an iteration through the columns, and this is row-centric. It's important that you use the row-centric approach and that you do not use the column-centric approach. That is, when you iterate through an array, you do so by having the outer loop iterate through the rows and the inner loop iterate through the columns. Okay? Now, why I say that is related to the way that the array is laid out in memory, and that's why I'm making a big deal about it. If I do it the preferred way, that way, then you can see that R starts with 0, and that C will go 0, 1, and 2, which just so happens to be a linear traversal through that array. It's going through each element contiguously. First, it gets this one, next it gets this one, next it gets that entry. When I now increment R to 1, and the column goes back to 0, I simply go to that entry. So I'm taking the entries from memory in contiguous order. In contrast, if I'm doing it in the column way, then the way I'm doing it is I start out with the column equals 0 and the row equals 0. So the first entry I take is this one. The next one I take is row equals 1. So the next entry I take is this one. Okay, and if there was more columns, then the next entry I would take would be that one. Why is that bad? Because there is something called cache memory. Did you cover cache memory in CS 130? Okay, so cache memory is very fast memory. It's faster than even RAM. So what happens when you are processing something like an array is the processor speculatively brings in more memory than just the one entry it needs. It brings in also contiguous blocks of memory on what are called cache lines. Well, if you're bringing them in and you're doing it in row-centric, then the cache lines, the next entry is already in the cache, the next entry is already in the cache. You're getting cache hits, and that's efficient. But if you're doing it in column-centric order, you may not get cache hits, especially if the array is much bigger than 3 columns. Let's say the array has 10,000 columns. It's probably not bringing in 10,000 elements on the cache line. So when you go from this entry to 10,000 entries later, you get what's called a cache miss. And the processor stalls while it goes out to RAM to get this entry. So the reason it's important that you do things in row-centric order when processing a 2D array is so that you can take advantage of this contiguous layout of memory, which means that you will be getting cache hits and you will be efficient. If you use the column-centric approach, you'll be jumping all over the array, which means you'll be jumping all over memory. And when you're jumping all over memory, you'll be getting cache misses, which is going to stall the processor. And your program will run more slowly. So use row-centric loops when you're processing your two-dimensional arrays. So questions about that? Okay. So what I want you to do now is there is a challenge exercise for today, which asks you to find the minimum and maximum values in a 2D array. So you should take advantage of the information I just told you in writing your loops. Please go to Canvas because this is a Canvas activity. If you go to the after class participation, you will see that there is a module for today called After Lecture 125 Vector of Vectors. Please click through and do that one. It's just one exercise. It's the challenge activity. Okay, if you don't have that on your computer, here it is. It's asking you to find the minimum and maximum miles. So I'm going to give you about, probably going to give you about 6-7 minutes to do this. Feel free to work on it with a neighbor. I'm just curious, how many of you are done at this point? Okay, in that case, we're going to go over it. For those of you who haven't finished, you can finish it up after class or finish it up along with me. So, I'm going to omit something first. I'm going to start by writing the loop. And you can see that they declared variables I and j for us. So we're going to use I and j because pretty sure that's what they were there for. I know I'm not doing something first, so I'm putting off initializing max miles and min miles. So all I'm going to do is have it run through the array. And here's the first important thing. I know that you can tell that the max number of rows and columns is 2. What did we tell you about hard coding in 102? Don't do it. Okay, there are some handy dandy constants here that you should be using instead. So those constants can be changed without causing your program to crash or produce incorrect input. So use those constants as your maximum values. Okay, so we're going to have an if statement, and we're going to say if miles tracker ij is less than min miles, then I want to set min miles to be miles tracker ij because it means that we found a new minimum. Okay, now I'm going to do something we don't want you to do. I'm going to have a second straight if miles tracker ij is greater than max miles, then we'll set max miles equal to miles tracker ij because that's the new max. Okay, now that should find, that's correct logically. So if the current entry is less than min miles, I reset min miles to that entry. If the entry is greater than max miles, then I set max miles to that new entry. But there's something important about what happens if I just run it like this without doing something else. What is this missing?
The minimum value.
I never initialized min miles and max miles. Now, you can see up here that they are initialized. Okay? But what happens if I leave min miles at minus 99? It will print out as minus 99 because there is no value in this array that is smaller than minus 99. Now, in 102, you may have been taught to change these things to very large values. So you might say, okay, I'll just change min miles to something very large, like 200. That's a bad approach. The reason it's a bad approach is, again, hackers. We talk about adversarial programming. So in adversarial programming, it's assumed you make the first move, which is I set min miles, say, to 200. Now the adversary is allowed to look at my code and devise input that will basically exploit it. So a hacker getting to look at min miles equal 200 will give me a whole bunch of data that's all greater than 200, thus causing my program logic to be incorrect. That's called adversarial programming. You make the first move, then a hacker is allowed to look at your code and devise the input so as to exploit it. So you don't really want to hard code values in here because the inputs may not correspond to the values you expect. That's why they gave you a hint. Assign with the first element in miles tracker before the loop. What they're saying is assign the first element in the data set. Initialize max and min to the first element in the data set. Once you do that, the hacker has no counter move. It's like checkmate in chess. If I set min and max. So what I need to do is set min miles to be the first entry, and I need to set max miles to be the first entry. And now the hacker has no recourse. I have initialized min and max miles to the first entry in my data set, and that is guaranteed to be a valid piece of data. Okay, no matter what other values are in the array, if this happens to be the minimum value, and all the hacker gives me for the remaining values is larger values, well, no problem. This was the minimum value, is correct. Okay, so that's what you should do when you're asked to compute min and max, which you are asked to do a lot in your career. So here's something that's worth writing down. When computing min or max, okay, initialize min or max to the first element in the data set. And you can't go wrong. Okay? So, it's always good to run it just to make sure that I didn't do anything silly. And it liked it, so we passed all tests. Now, there's a style issue here. Just like your English teacher is always on you about style, we will also be on you about style. Right here is a style issue. If miles tracker is less than min miles, then we assign the entry to min miles. If this condition is true, is it possible that this condition can be true?
Yes.
No, it can't be. It's impossible. If miles tracker is less than min miles, let's think about it. So let's make it the best possible case where the min and the max is initialized to 10. Anything less than 10 is going to satisfy this condition. So if this condition, if it's less than 10, how can something less than 10 possibly be greater than 10? It's impossible. It is, in fact, if this condition is true, because we know min miles must be less than or equal to max miles, right? That's the definition of min and max. Min miles must be less than or equal to max miles. So, if my entry is less than min miles, then it must be less than max miles, which means this must be false. It must be false. So stylistically, it's much better to say else, so that if this condition is true, this one is never evaluated. Again, efficiency. I know in this program it doesn't mean much, but if this is what is called a tight loop, a hotspot in your program, it becomes really important that you ignore the second test if it's impossible. Okay, so these are just things that make you better programmers. We do put an emphasis on efficiency because these small things add up. Okay, so this is ideally the way that you would write the code.
So that statement's being true, the else it's going to be skipped.
Yes. So if the question was, if this is true, then the else statement gets skipped completely. Okay? Because this else only executes if this condition is false. If it's true, the else gets skipped. Okay? So generally, when you have mutually exclusive conditions like this, you should use else if. Okay, and it avoids you doing things that can cause problems. Remember, in CS 102, we gave you an example of tax rate might be, say, 10% if the income is less than 10,000. It might be 20% if the income is 10,000 to 50,000, and it might be 30% otherwise. Okay, well, if you just write a series of if statements, if salary less than 10,000, tax rate equals 0.1, if salary less than 50,000, tax rate equals 0.2 if salary greater than 50,000, tax rate equals 0.3, well, you're going to end up with the wrong tax rate sometimes. If the salary is 5,000, what's the tax rate going to end up as? 0.1, that's the right answer. Is it going to end up as 0.1? No. What's it going to end up as? 0.2. Because you're doing these if statements serially, and this second if statement is also true. 5,000 is less than 50,000, so it sets the tax rate to 0.2. So using serial if statements when you have exclusive cases sometimes doesn't just result in inefficiency. Sometimes it means your logic is wrong. So it really is important that you use else statements when you have mutually exclusive cases. Okay, just getting used to it. Okay, so moving on, we have vectors of vectors. Okay, so a vector of vectors is like a 2D array, except that now it's written like this. Vector, vector, let's say it's a vector of ints. And one thing that's important when you do this is there needs to be a space right here. If you don't put a space right there, the compiler gets confused. So there doesn't need to be a space here, but there does need to be a space here. The reason is if you don't put a space, these two things are together. What might that look like to a compiler? It might look like extraction, the input operator. Whoops, compiler goes nuts. So you have to remember to put a space between it. There is a way around this that also can make things look a little more understandable. They're called type defs. Okay, so in today's notes, Dr. Plank has something on type defs right at the beginning of the notes. So you can make you can give a complicated type a simpler name. In this case, we didn't. We said that Fred is a new type, hence type def, and Fred will be an int. So now we could say Fred I, and what we're really saying is that I is an int. The compiler will go through and replace all instances of Fred with int. Now this is silly because Fred is not a very mnemonic name. We would always use int. But we can do something else. Let's say instead, yeah, nice teenage voice for me. How it did sound when I was a teenager. Not that high. Okay, so type def vector int. is an IVEC. So we're saying that we're defining a new type called IVEC. Okay, so here's our new type, IVEC. And now wherever we might want to use vector int, we can instead use the more succinct name IVEC. And not only that, we don't have to worry about that little situation of having to put a space between the rightmost two greater than signs. We can just have a nice tight looking type for this vector IVEC. And we named it something meaningful, so hopefully a reader knows that that means integer vector. 1 second. Whether you use, Dr. Plank likes type defs. I'm not such a big fan of type defs. I don't care whether you use them in your programs or not. I do care whether you can recognize them on exams. Okay? So whether you use type defs in your code or not, I'm agnostic on that. Whether you can recognize them on exams, I'm not agnostic. You better be able to recognize them on exams. They're just a simplification. Yes, I had to.
Do we have to type def outside of main?
Yes, good question. The gentleman's question was, do we put the type defs outside of main? Yes. These are global for the entire program, or meant to be global for the entire program. So please, in general, your include statements go first, your type defs and any constants go next. Okay, I know the book put its constants inside of main, but generally your constants also go outside of main, up here.
I just wanted to double check. I think I'm sure, but the type def won't replace it if it's in the string literal, like in the first example. You got the Fred named I is equal to still a little bit.
Mm-hmm.
We've replaced the first Fred with the set out statement. It's not replacing.
Very good, yes. In the second cout statement, because this is just literally Fred, so it will not get replaced. Yes. And you could really confuse matters by declaring Fred, but you shouldn't. Okay? So, and of course, you shouldn't ever. So, basically, all a type def does is declare a new, simpler name for a more complicated type, and then the compiler, wherever it sees that name, it will replace that name with the more complicated type, just filling it in. Yes?
I thought a program usually starts with an int min. Where is that int before the min?
Usually starts with a what?
Int min.
Like, where's the int before main?
Oh, good question. So the question was, I thought that main usually has an int before it. This is Dr. Plank in old school programming. This was not until recently have compilers started to enforce that main should return int. In the good old days, main didn't have to return, it was assumed that main returned an int. And compilers used to happily compile it this way, no longer. So these notes are from 4 or 5 years ago when the compilers weren't as strict. But yes, you have to put an int here. And this still always gets me. I'd say that 1 in 3 programs I compile, I forget to put int. And the compiler always complains these days. So good catch. I really need to remember. I'll try to go through the notes and correct these things. Other questions? Okay. So, you can, once you have set up a vector of vectors, you can treat it just like a two-dimensional array. So if I was trying to print out this vector VDM, I could print it out just like, or almost like, an array. I could say for row equals 0. Now, the vectors carry their size with them because they are variable sized. So I would say r less than VDM dot size, because that's the number of rows. And now for each column, I would say C equals 0, C less than VDM C dot size, because that's the length of that particular vectors. So what we have with a vector of vectors, each vector is its own vector. Okay, they don't even have to have the same sizes, unlike two-dimensional arrays where they're always square. Generally, our 2D vectors are also rectangular, but they don't have to be. Okay, that's why I didn't say VDM 0 here. I said VDM C because that gives me for each, so the first, this is VDM 0, this is VDM 1. So for each one, I'm asking it for the size of the vector in that particular row. So this one would return 4. Then when C is 1, it will return 3. When C is 2, it will return 5. Okay, and then I could simply say Cout VDM RC, just like, so I access the elements of a 2D vector just like I would a 2D array. The only big change is I'm using the size right here to control when I get to the end of the vector, because the vectors are variable sized. You'll be using 2D vectors in Lab 3, but you can also use them for the VFlip program in Lab 2. So, the big issue is how do we set them up? Okay? Because we can't declare that, we typically don't declare them in advance to have a certain size. Like in your Lab 2, you're given PGM files, and the PGM file contains the number of rows and the number of columns. So you know the number of rows and number of columns only after the program starts running. You don't know it when you write the program. So at runtime, you're going to have to adjust the image so that it has the right number of rows and the right number of columns. There's 3 ways we can do that. Okay? Here's the simplest way. We start, let's say, I'm going to change VDM to be, for Lab 2 purposes, let's say we call it a picture. Okay, a better name for Lab 2. So let's say you're doing VFlip and you have a vector of integer vectors, which is what you'll have. It's effectively a 2D integer vector. The first thing you could do is say picture dot resize rows. So that will make picture have this many rows. Now it has that many rows. Now we have to go through each column and each row and make it have the right number of columns. That requires a for loop. So for C equals 0, actually not C, we're going through the rows. Row equals 0, row less than rows, row plus plus. We are going to say picture R dot resize columns. And that will resize each row to have the correct number of columns. In this case, I'm making it be 4. So you might want to write that down because that will be code you can use in VFlip. So the first piece of code, again, let's do that quickly. The first one this one right here, resized picture to have the right number of rows. The second piece of code right there, I'm going to put it in right there, made each row have the right number of columns. So that's one way to do it. Okay? That's where we know in advance how many rows and columns we have. Now that's not always going to be the case. So if that's not the case, we have to improvise. Okay? So let's say instead that I know, actually let's go to the notebook. Let's say instead I know the number of rows, but I don't know the number of columns. Maybe I'm reading in student scores where each student has some number of scores, remember, on their line. So I'm going to claim that for some reason I know the number of students, but I don't know the number of scores for each student. So I might have a vector, and I'm going to use an IVEC again, of scores. And I'm going to pretend that I know the number of rows, so I can still say scores dot resize. I'll say num students. But I don't know the number of scores for each student. So then what I might have to do is something like this. For I equals 0, I less the number of students, so I'm going to read the students or process each student. And now I'm going to use pseudocode. Pseudocode isn't actual C++ code, but you could fill it in. And you got to get used to me using pseudocode because sometimes you want to express things at a higher level. It's a good way to also rough out a program. Okay, so I'm going to say something like, while more input for student I. And see, I'm pushing off. By writing the pseudocode, I don't have to worry about the messy details of how I'm getting that input for student I. I can just say scores of I dot pushback and whatever the input was. So what that is doing is one entry at a time, it is adding to that student. So initially, scores looks like this. And now when I process 0, the pushback is adding one score at a time until I get to the end of the input for that student. And at that point, I'll have the right number of columns for that student. Okay? So that works if I know the number of rows, but not the number of columns in each row. Now, it's pretty unusual that I'd know the number of rows, but not the number of columns. Typically, I know both the number of rows and the number of columns, or I know neither. Okay, like in this example, probably the number of students would also not be known in advance. So then there's a third way. And I'll show Dr. Planck's code for the third way. Okay, so what Dr. Planck is going to do is he's going to generate a whole bunch of random numbers. Okay. And we're going to pretend we don't know in advance either the number of rows or the number of columns for the random numbers. So here becomes the code that we would use. So now we're using doubles. So you'll see up here he has a type def for a dvec, a vector of doubles. And he declares a vector v1 of doubles. And he has his random number generator that he's seeding with 100. He's also declaring, well, we'll see, he's declared a vector which is going to store a row at a time. So dv, he's going to create a row at a time and add his row to his 2D vector. So v1 is a 2D vector, and what he's going to do is create one row at a time, create a row at a time in dv, and then add, and then push back, or then append dv to v1. So that's what he's going to do. Create a row at a time in dv, and then he's going to append dv to v1. So here we go. Now I know he's hard-coded 4 here, but that could be any number. So he's filling up the rows. He starts by clearing the vector because he wants to start the row from scratch. Then for each entry in that row, he creates a random number, multiplying it by 10, and pushes it onto dv. When he's done, he has a vector of 5 elements, but if he didn't know how many elements, he would have a vector of x elements. And he now pushes back that row onto v1. What that does is it copies the contents of dv into a new vector and pushes that new vector onto v1. So it literally creates a copy of dv. Okay? Not really efficient, it turns out. And that's the last lesson for today. So the last lesson for today is that this code is a large copy operation. This operation right here is a large copy operation. It's not bad when there's only 4 rows and 5 columns. I decided I was going to create some code that had 10,000 rows and 10,000 columns to see what would happen. And when I did that, it ran in 3.9 seconds. Okay, then I assumed that I knew the number of rows, but I still didn't know the number of columns. So this is my approach where I know the number of rows, but not the number of columns. So I still have to use pushback on the columns. And I ran it again, and I ended up with 3.3 seconds. So it was fully 15% faster to use the pushback approach than it was to use this copy approach. Okay? Now, let's say I knew in advance how many rows and how many columns I had. So instead, I could simply resize the outer vector initially, and then as I did each row, I first set each row to the final number of elements, and then I simply assign, because I've already created a vector of that size, I can now simply assign items to that row. That was the most effective. It ran in 2.5 seconds, which is a 36% savings over the 3.9 seconds. So the moral of the story is you want to avoid copying if at all possible, because in large programs, doing lots of copying is going to slow you down. Okay? Even this operation of pushing back can be slow in large programs or large vectors. Why is that? Because initially when you create a vector, it may give you only a small amount of capacity, like 4 elements. And then what it typically does when pushback exceeds the capacity and needs a fifth element, it doubles the size of the vector. But in order to double the size of the vector, it actually has to create a completely new chunk of memory, copy these 4 elements over to the new memory, and deallocate the old memory. Well, 8's not big enough to hold 10,000, so when we exceed 8, it will double it to 16. And again, it will copy the 8 elements to a new 16-element vector. So the problem is there's a lot of hiccups as it has to keep doubling the size of the vector. That's why pushback isn't as efficient as doing the resize up front. So bottom line, if you know the number of rows and columns in advance, which you will in VFlip because you will read it in, you can do the resize immediately. If you don't, you will have to use pushback to do it. Okay? So next time I'm actually going on Tuesday, I will probably have you do a short exercise where you use string streams and vectors, and then we'll move into the final review topic of the course, which is classes. And no, that's not true. We're going to move into functions next. So we'll move into functions on Tuesday.